This is a historical presentation because none of the work here is actually mine. So you made me go to the literature, and I'm very glad I did because I think that I managed to understand the reason why people have had so much trouble with these platinum hydrogen bands. What I would like to do this afternoon is to briefly look at the bands which are attributable to platinum hydrogen in the 2030 to 2100 centimeter region of the infrared spectrum, and talk about possible assignments, and then go into the pitfalls which have obscured the identity of these bands, primarily the role that water can play and also the possible contamination by carbon monoxide. And finally, what I would like to do is look at the energy loss studies and the neutron inelastic scattering studies, the recent studies, to see how these relate to the other work of Eichens and so forth. If you go to Hertzberg, that's a good place to start, and look for the region where you would see platinum hydrogen bands, there is a good correlation between the square root force constant and the ionization potential of the metal or a series of metal hydrides. And made some calculations here, looking up the ionization potential of platinum. It's about 9 volts, and if you go over here and back calculate the force constant, you find that there should be infrared bands due to platinum hydrogen between 2030 or between 2000 and about 2100 wave numbers. If you take into account anharmonicity, then you can get down to about 2030 wave numbers. So if you look at the first attempt to identify these platinum hydrogen bands, the first work, of course, was that published by Eichens and Pliskin. And there are 2 bands. The top is frequency in centimeters -1. They published their results in wavelength, so I changed this a little bit. And there are 2 bands, one which is due to a strongly bound hydrogen species, and the other which is due to a more weakly bound hydrogen species. This is in fact a deuterium. I'm sorry, this is a hydrogen adsorption. They're both shifted with deuterium, and they can be evacuated at room temperature, or at least the weakly adsorbed species, which occurs at about 2100 wave numbers, can be evacuated at room temperature, and you're left with a more strongly bound species. And then the question was, how do you assign these bands? And I would like to just follow the discussion of Bob Eichens. The first thing that comes to mind is that one has a heterogeneous surface with more than one crystal plane exposed. But I think that you can rule that out directly because it is the infrared band with a high frequency that is desorbed more rapidly. And if that is true, then it should be the low frequency band that should pump off at room temperature. So I think that we can exclude the possibility that we might have several crystal planes exposed. The other possibility is that there might be possibly a diadsorbed hydrogen species in the same platinum atom, and that should give you both a symmetric and an anti-symmetric stretching vibration, and perhaps one of the bands is due to two kinds of hydrogen, the strongly absorbed hydrogen plus a component of the symmetric anti-symmetric stretching vibration. But a careful analysis of the pressure dependence of those bands showed that there was only one band under the strongly absorbed species, a species which absorbs in about 20, 30 wave numbers. So that was excluded. And then the possibility arose that perhaps it's due to a hydrogen molecule ion. But if one equilibrates a 50-50 mixture of hydrogen and deuterium to about 46% HD, there was no band in the 5.4 micron region of the spectrum, which would be characteristic of an HD. And then Ishans came to the conclusion that that was not the answer. And he considered one additional possibility, and that was because we have talked with an we talked about an ideal mechanism for hydrogen-deuterium exchange, there's the possibility of a triadsorbed hydrogen species. If you do the deuterium study, the expected complex band structure does not occur for this type of a species. So I think that he safely concluded that this, well, it's not sure because the bands could possibly be weak, but he concluded that this was not probably one of the bands that he was observing. So there may be a Langmuir-Hinchelwood mechanism for hydrogen-bis deuterium exchange, possibly an Ely or ideal, but I think that the really ideal mechanism perhaps has not been defined yet. So Ishans then concluded that on the basis of these studies, there were two types of hydrogen that he was not able to identify the hydrogen species that were absorbed. We know that we cannot pump off hydrogen at room temperature, and therefore both of these bands could be evacuated at room temperature. Therefore, the infrared active platinum hydrogen probably represents a very small amount of the surface hydrogen that is actually chemisorbed. Well, following the absorption of hydrogen on platinum historically, the next series of studies which appeared were those of Ely. And he looked at the 2120 band, the high frequency band, and he found the same kind of pressure dependence that Ishans found on the 2120 band. But he also found that the intensity, the absorption rather, increased by increasing the extent of oxygen pre-treatment. And he concluded that perhaps, at least for the 2120 band and also for the lower frequency band, that perhaps the formation of platinum oxide formed by pre-treating the surface at higher and higher temperature, or with oxygen at higher and higher pressures, has something to do with the nature of the absorbed hydrogen. And the results that he obtained on the low frequency band were even more interesting. If you look at the spectrum over here on the right, this is the 2020 band. He exposed the surface to water at room temperature, and he found the 2020 band. No CO added, no CO presumably in the system. Hydrogen was not added, but he did find the appearance of this band in spectrum B, which is a low frequency platinum hydrogen band, presumably. And he found that if you increase the time of exposure, the band increased in intensity. And if you pump this off at room temperature, or even raise the temperature to 150 degrees centigrade and evacuated it, this band got even larger. So one has to worry then about the possible. He concluded, though, that this was probably due to the effect of water, and his suggestion was that water diffused to the platinum oxide interface, dissociated, and formed the platinum hydrogen species, which was hydrogen bonded to the hydroxyl groups of the support. That was Ely's conclusion, because he also found that for this band, the absorbance increased with the oxygen pressure dependence as the high frequency band, and therefore he concluded that water had a strong effect on the infrared spectrum of this yet to be defined platinum hydrogen species. He did the deuterium shift, and in his paper, he says that both of these bands with deuterium had the right pressure dependence. They don't look right to me. I find that the high frequency band increases much more rapidly pressure than the low frequency band. And if you deconvolute these, and he did not deconvolute his spectra, my impression is that his low frequency band is most likely a carbonate band. He said that no, it's not a carbonate band, it's the species that he was talking about. And he wrapped up his mechanism by suggesting the following in terms of the infrared assignments. The 2120 band was due to a hydrogen absorbing on a oxidic platinum patch due to improper reduction, giving rise to the 2120 band. And the low frequency band was due to the decomposition of water and an anion vacancy to form a platinum hydrogen site, which gave the low frequency band. And this band was supposedly greatly increased. The intensity was greatly increased by the presence of water. So those were Ely's conclusions. And these studies were followed up by a French group at Lyon, Limay, and they concluded something which was quite different. If you notice here, this is the absorption of hydrogen on platinum. The low frequency band was present even though there was no hydrogen added. You add hydrogen, you find an increase in the intensity of the high frequency band. And you can evacuate that at room temperature and pull that hydrogen off, but you don't do anything with respect to the low frequency band. But if you evacuate this overnight and you come back the next day, well, then the intensity of this band is increased tremendously. And not only has the intensity of that band increased, but you formed a new band. And if you've done any work on platinum alumina right away, you know that that is due to a bridge bonded CO species. It's a band at about 1880 wave numbers. And you could react that with oxygen and get the final spectrum. So they suspected that the band that Eli was reporting and Ishins was reporting at the low frequency band was due to a carbonyl or a CO contamination. And if they performed the study using deuterated material, the catalyst was prepared using the hexachloro deuterium platinum rather than H2PtCl6. They found that they were still observing the high frequency band, which was still there. The pressure dependence here appeared to be correct for the high frequency band, and that could be evacuated at room temperature. So they came to the conclusion that this band was simply due to carbon monoxide contamination. But in looking at their work, I seemed to feel that they wanted to make sure that this catalyst was contaminated with CO, because this is what they thought, and I'm sure it took no effort to get rid of the CO. Well, things had not yet, the answers to this had not really come to light yet, and the group at Johns Hopkins, just after I left, looked at this a little more carefully. Unfortunately, Dick Kokas died before this work was completed, but it was completed by John Ryder and Roger Barth, Dixon, and they were able, this bottom spectrum represents no effort at all made to try and eliminate contaminants, and then they had an oxygen-hydrogen sequential pretreatment in which they could clean up the surface reasonably well to give you spectrum B, which was free of any contamination by carbon monoxide. And whenever carbon monoxide showed up, they could get rid of it by this sequential oxygen-hydrogen treatment. And they looked at these bands rather carefully and found that essentially the same kind of information that Ishins had found, that you could absorb hydrogen at room temperature, it could be evacuated. They were basically two bands which agreed with the data of Ishins. You drop the temperature, the absorption would go up. And if you look at these quickly, the only thing that's really I wanted to point out here is that there's a difference in the pressure dependence. The high frequency band can be evacuated more easily than the low frequency band, and they are two different species. And if you look at the shift with deuterium, both bands shift and they show exactly the same pressure dependence. The 2120 and the 2060 band shift to 1520 and 1480, which means that they are probably due to platinum hydrogen. And they concluded, finally, that